So let's talk about setting up a test. Where do I start? How do I know where to start? I have a brand new product. I believe I've assembled it correctly. Where do I go? So one of the things we want to talk about is let's figure out a way to make a master part. Figure out if this part actually leaks or not. Now, there's an infinite number of settings that we're going to be able to use to determine if our part is leaking or not when we get to a production type speed. But if we're just starting out, we want to understand how our part reacts and what we're looking at for a baseline leak, we need to have some sort of a master part. So one of the tests we can do, and for example, I have here on the screen a basic test. We can create a test that we choose any parameters, and we can run this test multiple times to find out how good our product is. For example, I have this product here that I've just set on the bench, and I've just come up with a very simple test. What we can see is all of the settings that we need to do are on this screen now. So we have a test pressure that we're going to be going to of 10 psi, plus or minus a half a psi. Right now it's set to look for a 0.05 psi drop, but we'll ignore that for now because we're going to watch and see what happens to the rest of the test. On the right side of the screen, you'll see timers listed in 3 steps. We have a fill time that's going to pressurize the part. We have a settle time that allows any expansion or thermodynamics to calm down. And then we have a test step time where we're going to watch for a small decay. Then as a safety, we're going to allow the part to be vented so that the pressurized air, if an operator were to take a part off, it couldn't cause any damage. But if we're looking for a master part, one of the tricks I like to use is I'm going to take this vent time and I'm going to turn it to 0. And what we're going to do is go back out to the run mode and run a test. And right now you can see that we're filling. We draw a vertical line, we're settling now, just as it says on the screen, and we see the decay that happens during the test step. Now these were just random times that were chosen, but if we record the value, this value was a 0.0331 decay over that amount of time, but if we immediately start the test, the product was already filled and we left the pressure inside the part. So now instead of having to fill from 0 and come back up, we were pretty close to there. So you now notice we get less of a decay when we test it a second time, 0.0032. So not that the part got any better, but we left it pressurized so we could let the thermodynamics calm down of pressurizing the air and any compliance or any stretch that could be happening calm down. So if we record that value and run it again, what we should get is a very, very small number. With that, we can now say, okay, we believe that part to be a master non-leaking part. So now as we go to do the rest of our testing, we can say, okay, this is a great example of a non-leaking part. It was assembled correctly. It's not leaking any air. Now we wouldn't want to do this with production parts, have to retest them over and over. It's an unfair test to have to do it. But what we're going to do is, now that we know this part is good, we're going to use that to create a signature of what happens when I change timers. So if I quickly just come back in and turn some time on, and I'll just vent the test to get rid of the air that's in it. This is an example of the first time test. And what we'll see is that we still get some decay. But what we just proved is that the part does not have a leak. Now this decay is because of the thermodynamic process. If the part were soft, I could say that it was probably compliance or elastomeric creep causing the problem. But this is a stainless steel cylinder, so chances are it's not moving as much as the softer part would move. But now what we can see is that with these times that we have set, this is the amount of decay that we get off of a good part. If we were then to take a part where we had a manufacturing defect in it, where it was a missing O-ring or an ultrasonic weld that wasn't strong enough, or a solvent bond that wasn't thorough enough, we could then run that on the same test with the same setup and see, do we get more decay or less decay because of that manufacturing setup? Well, the chances are we're going to see more decay because air is actually leaving the product, where we know this was just happening because of a phase change. So we can actually change this and modify those times so that we can find the best results.